Hey guys, my name is Tiana, and this is my presentation on average rates of change and limits and continuity, which covers pages 151 to 159 in the resource guides. And I'm definitely going to be going back and forth between my slideshow and a whiteboard and Desmos. So, yeah. So first I'm going to be talking about the average rates of change. So how do we find the average rate of change between 0, 0, and 2, 4 on the parabola y equals x squared? So on a line, the average rate of change is going to be whatever the slope is. And y equals mx plus b, m is the slope, so m would be the average rate of change. But in a parabola, we don't have a specific slope because it's y equals x squared, but we can still find the slope of the line that is connecting these 2 points. So, yes. So we can use this formula to find the slope. That is, the slope is equal to y2 minus y1 over x2 minus x1. So we can plug in y2, so we can plug in the 4 as our y2 and 0 as our y1, and then 2 as our x2 and 0 as our x1, because these are our 2 points. And we should end up with 4 minus 2 over, or 4 minus 0 over 2 minus 0, which is 4 over 2, or 2, as our slope. And we also know that the line of this is just going to be y equals 2x, because there's no b in y equals mx plus b. We know that that's just going to be 0, because in this case it passes through the point 0, 0, so our y-intercept is going to be equal to 0. So I will show you this in Desmos. Yeah, so this is this line y equals 2x, and these are our 2 points. So notice how it passes through the 2 points, and it gives us the average rate of change between those 2 points on the parabola. So, okay. So this question is, find the average rate of change, or the slope, between x equals 2 and x equals 5 for the graph y equals x cubed minus 6x squared plus 4x minus 2. And I got this from the resource guides. So the second question is asking about the tangent line, which is going into derivatives, which I think Eli is covering in the next section, so don't worry about that part. Let's just find the average rate of change, or the slope, between these 2 points for this graph. So to do this, I'm going to go to the whiteboard. We need to plug in 2 and 5 into this to get our y point for each x value. So for x is equal to 2, we have 2 to the third power minus 6 2 squared plus 4 times 2 minus 2. And we can solve that out. So 2 to the third power is 8 minus 6 times 2 squared, and 2 squared is 4, and 4 times 6 is 24, plus 4 times 2, which we know is 8, minus 2, and I believe that is 16 minus 26, so negative 10. So that would mean our first point is 2, negative 10. And now let's find our second point with plugging in 5 into this problem. So y is equal to 5 cubed minus 6 times 5 squared plus 4 times 5 minus 2. So 5 squared, or 5 cubed, sorry, is 5 times 5 times 5, so that would mean 25 times 5, which is 125. Minus 6 times 5 squared, which is 25, plus 4 times 5, which is 20, minus 2. And 6 times 25, I believe, is 150. Yeah, so 125 minus 150 plus 20 minus 2. So 125 minus 150 is negative 25 plus 20 would mean negative 5 minus 2 is negative 7. So that would mean our second point is at 5, negative 7. So now that we have the y value for each of these points, we can use the formula y2 minus y1 over x2 minus x1. So, well, it doesn't really matter which one's 2 and 1, but I'll just use this as our 2 and this as our 1. So negative 7 minus negative 10 over x2, so 5 minus 2. And remember, when we're subtracting a negative, then they both become positive. So negative 7 plus 10 is 3, divided by 5 minus 2 is also 3. So our slope is actually equal to 1. And remember, y equals mx plus b, our m is 1, so that would be y equals just 1x, or x plus b. And we want to find the equation of this line. So if we have the slope and we have points, we can find the y-intercept. So we can just plug in two values. I'll just plug in the 2 and the negative 10. So y is negative 10 when x is 2. So that means b is equal to negative 10 minus 2 from both sides, negative 12. So our final equation, sorry, I'm running out of room, is going to be y equals x minus 12. And this is the equation of the line that connects these 2 points on this graph. And I'm going to show this graphically in a second. So let's go back to Desmos. So as you can see here, wait, this is the wrong one, sorry. Here is the graph of the function that we were just working with. And we found the values, we found the points at, when x is 2, it's at negative 10. And when x is 5, it should be at negative 7, around there. So if we want to connect these 2 points, this is the line we came up with. And as you can see, it connects the points to negative 10 and 5, negative 7 on this curve. So it shows the average rate of change for these 2 points, even though this line is quite different than the parabola, or not parabola, sorry, the function. So this is the line of the average rate of change. Okay. And we're ignoring the last part of this question. Okay, so the next thing I'm going to talk about is limits, which is calculus. So the limit of a function f of x as x is approaching a on the x-axis is equal to L. So what this means is that as x is approaching a on a function, what is the y value getting closer to? So I'll show a more graphical approach to this. So find the limit of this function that I graphed here, x squared minus 4x, as x is approaching 2. So as x is approaching 2, what is happening to our function? Well, it's getting closer and closer and closer to this value, negative 4. And notice how this is true for both sides of the function. Yes, it is true that if we plugged in 2 into this function, we would get negative 4, but that doesn't mean that we can do this for all limits. I'll talk about that later though. But looking at the graph, this limit is negative 4 because as x approaching 2, the graph is approaching negative 4. Okay. Now, here is a more weird graph. So what is the limit of this function as x is approaching -4? So as you can see, on the left of -4, well, we kind of have two different parts of -4, and this part has a hole, this part has solid dot. From the left, we're getting closer and closer and closer to 3. So the limit from the left is equal to 3. I'll talk about one-sided limits in the next slide. And as we are coming to -4 from the right, we're getting closer and closer and closer to -2. So notice how the limit on the left is not equal to the limit on the right. So that means that the limit of f of x as x approaches -4 does not exist. And we can write this as dne, because if the left-hand side is not equal to the right-hand side, the limit doesn't exist. Okay, now we're going to find the limit of f of x as x is approaching -1. So -1 is right here. What is happening to the function at -1? Well, from both sides seems to be approaching the same thing, which is 4. So this limit is going to be 4. Now what about as x is approaching 2? What is happening to the function? So as we get closer and closer and closer to 2, it is getting closer to -1. But that is only on the left. On the right, as we get closer to 2, it is actually approaching 5. So again, the left-hand side does not equal the right-hand side of this limit. So that means that this limit does not exist. Now, what about as x is approaching 4? Notice how f of 4 is undefined. We have a hole here in our graph. But this isn't asking for f of 4. This is asking for the limit as x is near 4. As x is getting infinitely close to 4, what is happening to the function? Well, as we get closer and closer and closer to 4, it is approaching 2. And this is true for both sides. Doesn't matter that f of 4 is undefined, the function is still, the limit of the function as x approaching 4 is still going to be 2. Okay, here's another example, except this part goes into one-sided limits. So I said in the last slide that the limit does not exist if the left-hand side does not equal the right-hand side. But there's also a thing called one-sided limits, and you can tell if it's asking for the one-sided limit because there's either a minus or a little plus that comes after the number. So the minus means as we're approaching the value from the left, and the plus means as we're approaching it from the right. So in this case, it's saying, what is the limit as x is getting closer and closer to 0 from the left, because we have this negative. So we can ignore the right-hand part. As we're getting closer and closer to 0 from the left, well, our function is approaching 0. So this limit would be 0. Now, what about if we're approaching 0 from the right? Well, in this case, the function is getting closer and closer and closer to 2. So this limit would be 2. Now, C is asking for the limit of f of x as x is approaching 0. Well, if the left-hand limit does not equal the right-hand limit, which in this case they are not equal, then the limit does not exist. So this limit, we can write dne because it doesn't exist. Now, what about if x is approaching 2 from the left, because we have this minus? Approaching 2 from the left, the function is getting closer and closer to -2. So this would be -2. Now what about if x approaching 2 from the right? So as we're getting closer and closer and closer to 2 from the right, it is approaching 0. So that would be 0. And then what is the limit of f of x as x is approaching 2 in general? Well, again, the left-hand side of the limit is not equal to the right-hand side of the limit, so therefore this limit does not exist. And okay, this is asking for as x is approaching 4 from the left. So same thing from the left, as we're getting closer and closer to 4, the function is getting closer and closer to 4 as well. Sorry. Okay. And what about from the right? Well, as we're getting closer and closer to 4, the function is also approaching 4. Again, it doesn't matter that there's a hole there. It doesn't matter that f of 4 is undefined because it is still approaching 4 near as x is approaching 4. The function is approaching 4. It doesn't matter that f of 4 is undefined. So notice how in this case, the left-hand side of the limit is equal to the right-hand side of the limit since we said that they're both equal to 4. So that means that the limit as x is approaching 4 from both sides is also equal to 4. So this one does exist. Okay. Now I'm going to talk about continuity. So this is how the Aca Deca resource guides defines continuity, which is different from how my calculus teacher defines it. Anyways, so the graph is continuous if at each x value where the graph exists, the limit of the graph agrees with the value of the graph for the x value. So the limit of f of x as x approaches c is equal to f of c. And that would mean that the graph is continuous. So is this function continuous? Another way to imagine continuity is a graph is continuous if you don't have to like pick up your pencil to draw, to do like a break in the function or an asymptote or a hole. So if you have to pick up your pencil, then that would mean that it's not continuous. So in this case, well, it seems pretty continuous, but right here at 2, we have a hole, and f of 2 is actually equal to 5. And we can see this graphically, but symbolically, it says the limit has to be equal to the value. So what is the limit of this function as x is approaching 2? Well, from both sides, it is actually approaching 3. So the limit as x approaches 2 is 3, but what is the value of f of 2? It's actually equal to 5. And this value is not equal to the limit, so this would mean that it is not continuous. Okay, and normal polynomial functions are continuous, so we can use a process called direct substitution. So remember, if it's not continuous, that means we have an asymptote or a break. Like a log wouldn't be continuous. If it's a fraction, then there's often going to be either holes or asymptotes. But a polynomial like this one, which I got out of the math practice test, is going to be continuous all the way. It's not going to have any holes or breaks or asymptotes or gaps. So we can use this process called direct substitution, and this means that we can substitute the a value, the value that x is approaching, into f of x. And this doesn't work with functions with any holes, breaks, or gaps. So I will write this out. Second, sorry. So for this one, that means that we can substitute 2 into this equation. So I will go do that on my whiteboard. So our function is negative 2x cubed minus 4x squared plus 2x plus 4, and we want to find the limit as x is approaching 2. Lim as x approaches 2. Okay, And we can use direct substitution since this is continuous. So that means that just substitute 2 in. So 2 to the third power is 8 minus 4. 2 squared is 4 plus 2 times 2 plus 4. So negative 2 times 8 is negative 16. And negative 4 times 4 is negative 16. And then we have plus 4 plus 4. And if you solve that out, you have negative 16 minus 16 plus 4 plus 4. It should be negative 24. So this would be the limit. And it is pretty simple. But in a lot of cases, the limits, you can't just take whatever x is approaching and put it into the function. But since I looked at the Aca Deca practice test, and this was actually one of the only limit problems that was even in there, so I don't think you're going to have to know the more complicated ways where direct substitution doesn't work. If it's a polynomial and you don't end up with division by 0, you can definitely use direct substitution and it will just get you your solution for the limit. It's a pretty fast way to do it. And I'll show you guys this graphically as well. So on Desmos, oh, never mind, I didn't have this in my graph, but as x is approaching 2, it should be approaching that value that we just found. So next, I'm going to talk about infinite limits and asymptotes, which is a little more complicated because you can't necessarily use direct substitution. And I got this problem from the Aca Deca resource guides also. So this is y equals 1 over x, and it says discuss the continuity and interesting limits of this function. So remember, the graph is continuous if you don't have to pick up your pencil at all when drawing it. And notice how here, since f of 0 is actually undefined, because we have a vertical asymptote here. So f of 0 is undefined, and we would have to pick up our pencil because we're getting infinitely small. Then you have to pick up your pencil over here, and where we're infinitely big because the asymptote, because there's an asymptote. So that would mean that this function is not continuous, but we can discuss the continuity by saying, where is this continuous? Well, it's continuous on the interval negative infinity to 0, union, which means and, or from 0 to positive infinity. So the only place where it's not continuous is at 0. And that is because we have an asymptote. So now I'm going to be going into these more complicated limits. So we're not going to do a graphical approach to this, because what if we didn't know the graph? So we can try and use direct substitution. It's not going to totally work, because if we, as x is approaching infinity, what is happening to 1 over x? So imagine plugging in infinity for x. That means that our function is going to 1 divided by infinity. And we can't really do that. But as x is getting infinitely big, like let's say x is equal to 1 million. It's getting closer and closer to infinity. What is happening to our function? It is going to be 1 over 1 million. What about if x is equal to 1 billion? Then our function is going to be 1 over 1 billion. So it's getting smaller and smaller and smaller and smaller, and it is approaching 0 as x is approaching infinity. And we can see this graphically too. As x is going to infinity, the function is going closer and closer and closer to 0. So what about as if x is approaching negative infinity? So if we plugged in something decreasing without bound, like negative 1 million, then what is happening to the function? It would be negative 1 over 1 million, which is a very, very small negative number. Now, what if x is 1 billion? Then it would be 1 over 1 billion. So it's getting really, really, really small as x is going to negative infinity. And this time it is approaching in a negative way. So instead of coming down on the asymptote like this, it is coming up from negative, but it is still going to be approaching 0 as x approaches negative infinity. And graphically we can see that this is because we have a horizontal asymptote here, so it's approaching 0 on both sides. So both of these limits are equal to 0. Now what about as x is approaching 0? We have 0 from the right and 0 from the left. So if we tried to plug this in for direct substitution, we would end up with 1 divided by 0, which is undefined, as we know, so we can't do that. But we can think of it as if we're getting really, really close to 0 from a positive direction, from the right, from the right, then let's say we're going to have a really, really small fraction, like 1 divided by 100. So let's say we plug that in. I'll go back to my whiteboard. Lim as x approaches 0 from the right of 1 over x. So 1 over 0, undefined. But that doesn't mean that the limit is necessarily undefined. Yes. Okay, so what is something really, really, really close to 0 from a positive direction? I'm going to use 1 divided by 100 for x. That would mean that the function is 1 over 100, which is actually just equal to 100. Now, what about if x is equal to 1 over 1,000? Or 1 over 1,000, sorry. Well, we can plug this into our function. So it's 1 over 1,000, which is equal to 1,000. So as you can see here, as x is getting closer to 0, our f of x value is getting infinitely big. So that would mean that this limit is equal to positive infinity. Now, what about from the left? X approaches 0 from the left, 1 over x. So, well, again, if we tried to plug in 0, it would be undefined. So that wouldn't work. So instead, we just have to think of what is happening near 0, because the limit isn't asking for f of 0, it's asking for what is happening as we get really, really, really close. So in a negative direction this time. So in this case, something close to 0 that is negative, well, would be if x is equal to negative 1 over 100. So if we plug that into our function, 1 over negative 1 over 100, which is equal to negative 100. So notice how this is negative, whereas this one's positive. So this one is decreasing without bound or approaching negative infinity. I'll show you with if x is equal to negative 1 over 1,000. We can see that the function, if we plug that in, negative 1 over 1,000, which is equal to negative 1,000. So this time it is decreasing without bound, whereas before it was increasing without bound. And I'm heading back to the graph here. So, yes, as we can see from the left, it is approaching negative infinity, and or 0 from the left approaching negative infinity, and 0 from the right approaching positive infinity. So the limit of as x is approaching 0 in general, we would actually say does not exist, because remember, if the left-hand side is not equal to the right-hand side, then the limit doesn't exist. But the one-sided limit still exists. This one's infinity and this one's negative infinity. And sometimes asymptotes can still get limits that do exist. Like, for example, in some graphs, that it is approaching positive infinity from both sides, or it's approaching negative infinity from both sides. So in that case, the limit could just be positive infinity or negative infinity, whereas this one, it doesn't exist, but the one-sided limit still exists. So that's all for my presentation, guys. I hope you enjoyed and learned a bit. If you have any questions, please email me, or if you want me to go more in depth onto limits or do more presentations on it, I'd be happy to do so. I don't think that there's going to be a lot of limit questions, because I looked at the practice tests and they are mainly on geometry and probability, and there's only a couple calculus questions, and I think for most of them you're going to be able to use the techniques that I went over today. So that's all, guys.